The assignment that is due today is 5.5, and 5.5 is on optimization. What is optimization? Well, the idea of optimization is that we can consider all of the different possible outcomes for a particular situation, and there might be one that has, out of all those different outcomes, there is one that gives us an optimal outcome versus maybe a minimal outcome. Depending on the situation, one might be more advantageous over another. For some situations, I might want something, maybe for I might want the largest box possible for a particular volume, or maybe I'm looking at the smallest cost for something. So maybe we're looking at, with the box example, that would be the optimization would be a maximum versus the cost, trying to look for the minimal cost for a company, because of, you want to have the highest revenue for your company. And so you are going to, it's advantageous to get a minimum for certain prices. So optimization is a mathematical technique for finding a maximum or a minimum value of a function. Consider this. Let me zoom out so you can see, if for those of you who are still copying, what optimization is. Here is an example. Now I'm going to cheat because I have some tools in Microsoft Paint, bless you. Here is my example. It seems a little large. I'm cheating big time. All right, so I have, this is a cardboard sheet. This is my example. It is a cardboard sheet that measures 25 inches by 40 inches. This is a piece of cardboard. Now, what I want to do is I want to cut off the corners of this cardboard. And if you can imagine, after I cut off those pieces, I'm going to rotate these side lengths upward to create a box. It's going to be a box without a lid, but that is okay. So my goal is to fold this up. If you can still imagine what happens when I do that. I'm folding these, I cut these off and I fold these up. That would give me a box that looks more or less like this. Can you envision it? Yes, no, maybe so. I'm cutting out these corners right here. And then I'm going to fold up these sides here to get something like this. Do you see it or not? Okay. So what I want to do is I want to find the value. If I cut out these corners here, I'm going to cut out, is this going to be a rectangle, or is it going to, a square is a rectangle, but is this going to be a square or more like a, a rectangular shape? Doesn't it have to be a square so that this side here will measure up with this side here when I fold it? So we're looking at a square, and I'm trying to figure out this length here that I'm going to cut out, X, for all of these. And I want to know what is the maximum volume that I can get from this, this cardboard piece. What is X to get the maximum volume? Everybody caught up? All right, well, if I need to find X to get the maximum volume, then I probably need to know the volume equation. This is called a rectangular prism. Do you know what the equation for the volume of a rectangular prism, what that is? Do you know the volume of a rectangular prism? What is it? Width times length. Isn't width times length, isn't that two-dimensional? Yeah. So we're going to take our width times the length times the height. I am just going to say this is our length times the width times the height. So I don't care what you call these, whether this is the length and that's the width or whichever, but it's multiplication. Multiplication follows the commutative property. So the order doesn't really matter. So if I consider, if I fold this up like this, where's X? Yeah, this would be our height. So I'm going to label that X. Is there any way that we can figure out maybe what goes here, what that length here is? From what we're given? Yeah, so this would be 25 minus 2x. Where did you get the 2x? Was that Emerson? Yeah. Emerson, where did you get 2x? Yeah, so what you're saying is this length right here is 25 inches. And if I take, so that means that this length here is 25 minus this x and minus this x, which is the 2x's. Is that right? Okay. So what is this length here? 40 minus 2x. Yeah. 40 minus 2x. So all of this length right here is 40. And then minus this x and minus this x would give us minus the 2x's. Okay, is everybody following? Is anybody confused with how I got these dimensions? Now what I want to do, is that too small when I zoom out that much? What I want to do is I want to take these dimensions and plug them into my equation. So volume becomes what? X times 40 minus 2x, okay, times 25 minus 2x. Now I want to find the maximum volume. How many volumes does this give me? How many volumes does this equation give me? How many different values of x can I plug into this? Yeah, any real number. Well, there might be some limitations, right, on how many, you know, as far as the length of the cardboard is. I couldn't cut out 1,000 feet, right? Because, right, or a negative value as well. So there are literally infinite. Doesn't this represent infinite volumes? Infinite potential volumes, and I want to find the maximum volume. How do we find maximum? Consider the things we've already talked about in chapter 5. In the section 5.1, 5.2, 5.3, and 5.4. What were we talking about that might be able to give us a tool on how to find the maximum volume? The first derivative test. What does the first derivative test tell me? Yeah, it'll tell me, I can use the derivative, which is the slope, and find if the slope is positive, 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 followed by a negative, 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 then whatever this point right here is, that is my maximum. So we're going to take the derivative of this. How do we take the derivative of this? We could use, actually, this would be the double power rule, which we haven't learned, that goes beyond the course, the double power rule. I guess you could reason through how to do the double power rule. But we don't have to use the power rule at all. Any suggestions on how to do this without the power rule at all? Just because the power rule, I mean, it just gets, there's nothing wrong with the power rule. I like the power rule, but you'll end up with something that might be a little bit harder to find the x value when the volume is 0. Okay, so so distribute. So let's distribute. And so that's going to give me, right now, I'm not doing any calculus at all. In fact, this skill right here, you learned in probably 7th or 8th grade, the distributive property. And then you did it again in secondary math 1. And then when we distribute here and here, that's a secondary math 2 I did, because we have a binomial times a binomial. So let's do this first part here. That's going to give us 40x minus 2x squared. So I have this binomial times this other binomial here. So now we'll have to use, some of you learned this as FOIL, so we'll have to do that. No, I think I'm just getting sloppy. So what is 40 times 25? 1,000. So I'm getting 1,000 x. What about if I distribute here? What is that? 40x times negative 2x. Negative 80x, x times x squared, okay. Now I distribute here and here. What's negative 2x squared times 25? Okay, and then distribute here. Is that positive? Negative times a negative is a positive, positive 4x cubed. And that equals my volume. Right, now what? Yeah, combine like terms. That gives me that the volume equals 1,000x minus 130x squared plus 4x cubed. Does that look right? Okay, now what? Yeah, let's use the power rule. When I use the power rule, so now we're using calculus. When we use the power rule, what does this become?
160x plus 112x2
Squared.
squared.
Okay. And that equals what?
Yeah.
It equals 0, yeah, because we're trying to, this is an optimization problem. I'm trying to find that maximum volume. So what kind of function is this? What function family does it belong to? Is this linear, exponential, quadratic, cubic, quartic? What kind of function family is this?
Yeah.
It's cubic, yeah, it's cubic. And so we're looking at something that probably looks like, I don't know, maybe, let's do this. Maybe something that looks like this. And I'm trying to find that maximum volume. What kind of function family does this belong to? That's, yeah, it's quadratic. It's quadratic. All right, so how do we solve for x? Yeah, I think using the quadratic formula would be a great idea. If I'm going to use the quadratic formula, what is the quadratic formula? Nice. Good job. Who was that? That was Chris? Awesome. Good job. Over 2a. Nice. Well, what are my ABC values? Yep. Yeah, correct. So we're going to throw these values in. So I have negative b, which is negative 260 plus or minus the square root of negative 260 all squared minus 4a c all over 2a. Okay, so we have a plus, negative, negative, which makes a positive. So that part here becomes 260 plus or minus. What's anybody have a calculator? What's negative 260 squared, all squared? 67,600.
Yeah, 67,600.
Oh, 67, not 27. 67,600. Okay, and then this mess here. Four times 12 times 1,000. 48,000. All over 24. Okay, so that gives me 260 plus or minus the square root of what's this in the square root? Is it 19,600? Is that right? Did I do the math right? Okay. All over 24. And so this is going to give us what? And use parentheses so I can do this twice easily. I'm getting 16.66 bar. And what? And 5, yeah. Actually, these are not approximations, these are exact. Okay, we have 2 answers. If we have 2 answers, but yet we have this maximum, we have this one maximum here, it probably means one of these is not allowed. Now, what we could do is we could do, in fact, what we could do is go ahead and do a what is this called where we put in our values here? Yeah, this is our sign diagram. We could try to figure out what's happening in between. In fact, my guess is one of these is a minimum and not a maximum at all. So how do I figure out, actually, let me just import our equation. This is our, I'm sorry, I should have said this was V prime. Uh-oh, no, that's not V prime. This was a V prime right here. So here's my equation. That is my derivative, and a derivative represents what? Yeah, this is my instantaneous rate of change, and I'm trying to figure out what my rate of change is for all these different intervals. So this is my slope equation. So we should try what for this interval over here? Try what? 4. Okay. If I plug 4 in for here and here, this part here becomes what? It's a positive. Yeah, but we also have then we'll have a negative here. We need to know, does all of this stay positive, or is this large enough to make it negative? If we plug in a 4. Well, 4 squared gives me 16, and then 16 times 12. And then we still have this 1,000 over here. To me, it looks like it's going to be positive. That 4 times the 260 might give me something close to 1,000, right? A negative, close to a negative 1,000. And here I already have 1,000. And so then I have a bunch more here. So logically speaking, without even using a calculator, it seems that this would be plus. Are you guys okay with that? Okay. What about for this interval here? Okay, let's try x equals 10. I'm going to plug that into here and here. And the question is, does all of this stay positive or does it become negative? If I plug in 10, 10 squared is 100. Does that look right? So is this positive or negative? It's negative. And then something over here. 17. Okay, so plus, so we're going to try 17. We'll throw, how about something, sure, let's do, I was thinking maybe 20, something easier to calculate. So if I plug in 20 there, that gives me 1,000 minus 5,200. Does that look right to you? I'm just doubling this because before I put 10 in. Okay. And then if I plug, and then this gave me 1,200 when I plugged in 10, but if I plug in 20, don't I multiply that by 2? Does that sound right to you? You guys okay with my math? Oops. Plus 2,400. What is it? 4,800. Oh, because I put in the 20. Oh, yeah, because that 20 times 20 is 400. So that would, I'm multiplying by a 4 and not by a 2. So 4,800. Yep. Is that going to be positive or negative? Yeah, it looks like it's going to be. Is it negative? I take this positive and add those together. Is that positive or negative? Yeah, it looks like to me it's going to be positive. So that's going to be positive. So what's happening when x equals 5? This is a max. And this over here, it's a min. Now, I want to, so the answer has to be what? 5 gives me a maximum. Does this 16.6 even work? Let's go back up to our box over here. If x is 16.6, can x be 16.6? 16.6666. Why not? Yeah, there's not enough corner to cut off here. If I have 16.666 times 2, that gives me, for this part right here, 25 minus 2 times 16.66 bar. That's going to give me 33.3. Did I do? No, I don't think I did that right. Wait, hold on a second. 25 minus. This is what it gives me. Gives me 25 minus 33.332. So there's not enough fabric or enough cardboard to cut off. So it can't be, this value can't be 16.66. Okay, scrolling down. So yeah, the answer is, oh, so what did it ask? It says, what is the value? What is x to get the maximum value? Emerson, can you step me through what I did? So we started out with this cardboard. The dimensions were 25 times 40. And I don't want you to do the math. I just want you to step me through the logic of trying to figure out the maximum volume. What did we do?
So first we we used the variable x and then put it into an equation for volume.
We had to find the dimensions of the box, right?
Yeah.
Okay.
Yeah, we knew the dimensions of the box, I guess. Like, yeah, we figured out the dimensions of the box based on our variable x.
Okay.
And then we use that to make it into a volume equation.
Into a volume equation, okay.
And that's sort of like, in this situation, it was like our position.
It's like our position function. I agree with you.
And so, then we use we got the first derivative of our volume equation so that, then we could find where the slope was 0.
Where this, yeah, we had to find the position. So we found the derivative and we had to find where the slope was 0. Okay, good.
And then once we found where the slope was 0, we had 2 different points where it was at 0, and we knew that one of them would be a maximum and one would probably be a minimum. And so we used the sign diagram to find which one was the max, and then the min ended up not being something that made sense because we looked at the box completely. So.
Perfect. Good. Nice work. Okay, so when you do these the optimization, normally there are 2 different equations. I want you to think about that normally there are 2 different equations. In this case, we had to figure out these pieces here, which would be considered our first equation. And then we had to take those values and plug them in to our volume equation. What told me that I was going to take the derivative of volume? What specifically in our question told me I was going to be taking the derivative of volume?
Asking for the maximum volume.
Yeah, it's asking for the maximum of the volume. So that would mean that we're talking about, we have to take the derivative of that. So I'm going to graph this. I'm not super happy with how the graph looks for this because the value seems so scrunched together. But our equation, oops, that is not what I meant to type in. So we have our volume, we'll just call y equals x times 40 minus 2x times 25 minus 2x. And there's our graph. Oops. It does not look pretty. In fact, how far does this shoot up? So here's my representation here. I go up and back down and then back up. So it's so scrunched together, it is harder to see. And I can see up here, this is where our turning point is. Right here at x equals 5. So x equals 5, what does 5 represent? What does y represent? What does the vertical axis represent in this particular problem? If this is our equation, what does y represent? It's the volume, yeah. So when x is 5, our volume is 2,250. And then the graph, so the graph goes all the way up and then it goes back down. So if I go all the way back down here, we can see that we have this minimum point. And if our x is 16.667, then the volume is what? Does that make sense that a volume would be negative? No, volume in fact has to be positive. There's certain quantities that always have to be positive. Speed always has to be positive. Distance always has to be positive. Volume has to be positive. So yeah, this doesn't make sense to have a volume that is negative. Okay, we're going to do another one. What's the main idea today? Optimization. That's what we're doing. These are optimization problems. Okay. Here is the example. I have a barn. And I'm going to use the side of the barn as one of the sides of a pen for my horses. There's my horse pen. And this is going to be a rectangle with a base of X and a height of Y. And my goal is, I really want to make, I'm limited on the amount of fencing that I have. I don't have a lot of money. So the most I was able to purchase fence-wise for my horses was 500 feet. So the total fence the fence length is 500 feet. I want to find my X and Y value that will give me the maximum area for my horses. What is X and Y for the max area, and what is the area? Is it possible to arrange my fence so that I have a rectangle with 0 area? Is it possible to arrange this fence so I have no area at all? Yeah, so here, yeah, so here's one fence side here, that's 250. And then the other one here is 250. There's no more fence for the Y value. And so there's no area then. So I'm looking for the maximum. What is the maximum area that I can, what does X have to be so that I have a maximum area? Does everybody understand the question? Does anybody have any suggestions of how to go about finding this answer? Can you think of any equation that I need? Andrew, can you think of any equation that I need to solve for this?
Not too sure on this one.
Well, it does say something here that gives us a hint. Yeah, what's the area of a rectangle? Length times width, or base times height, however you prefer to remember it. So we're going, one of our equations is going to be area equals what? In this case, area will be what? X times Y. Now, I guess I could take the derivative of this and maybe use the implicit differentiation, but then I'll have usually a Y prime in there. And so I have to find the slope of Y, which is just going to make it more difficult. So there's got to be another equation that I can come up with where I can substitute something in for Y so that I only have one variable. Can you think of another equation that I need? Yes.
Would it have to do with like the perimeter, like 2x plus 1?
Yeah, perfect. Is that Sam?
Ellie?
Oh, it's Ellie. Good job, Ellie. So the perimeter. So the perimeter then of this is going to be what? We know it's 500, but what would my equation be?
2x plus 1.
Yeah, 2x plus y equals 500. Which of these equations am I going to take the derivative of? The perimeter? Does that sound right to you guys? Am I going to be taking the perimeter of the area, the derivative of perimeter? Why not?
Still asking for area.
Yeah, I want to find the maximum area. So I'm going, that means that I need to find with the area is quadratic. So we're looking at a parabola. So there's this graph here, that's a parabola. And whatever that highest area is, that's what I'm trying to find. I'm trying to find that X value that will give me that highest area, that max. Yeah. Is that Chris? Chris, look how smart you can be when you're not on your book or reading your book. Right, so Chris said, what if we rewrite this in terms of Y, and then whatever that Y equals, we just plug into here. I think that sounds like a brilliant idea. So we have Y equals 500 minus 2X. And then if Y equals this, it means Y is this quantity. So we'll just take that and plug it right into our other equation. So I'll use a different color. And so I have the area equals X times 500 minus 2X. Now what? All right, let's distribute. If I distribute, that's going to give me that the area equals 500x minus 2x squared. Now what? Take the derivative, okay. So we're gonna take the derivative. If I take the derivative of our area, what do I get? Minus 4x, okay. Now what? Set it equal to 0. I want to know when the slope of my quadratic is 0. So I'm going to make this 0. 0 equals 500 minus 4x, okay? And now? Solve for x. How do I solve for x? Subtract what? All right, so that gives me negative 500 equals negative 4x, okay? Okay, that gives me that x equals what? 125. Is it guaranteed that this is a maximum? It could be a minimum, right? Or it could end up being a stationary inflection point. Actually, I know it's quadratic. There's no stationary inflection for a quadratic. How can I, so what do I do to ensure that this is a maximum? We have to use a sign diagram. So this is our x value of 125 and how, so what should I test over here? 100. What do you hate about 0? If I can select anything below 125, wouldn't 0 be a nice handy number to pick? Try x equals 0. If I plug 0 into my derivative here, what does that give me, a positive value or a negative value? I take 0 and I plug it into here. So this becomes 0. Do I have a positive or negative value? Yeah, I have 500, so that's positive. What should we try over here? Try x equals what? 200, okay, 200. If I take 200 and I plug it into here into our derivative function, 200 times negative 4 gives us negative 800. Is that positive or negative? Yeah, it's going to give me, in that case, negative 300, so negative. If we have a slope that is positive followed by a negative, what is that? It's a maximum. We have just ensured, we have confirmed that this point here is a max. Okay. So did we finish? Did we answer the question? It says, what is x? Oh, what is x and y? Yes, sir.
I'm a little confused because I thought that we would be, there's only like 3 sides that we're actually putting fencing on, right?
Uh-huh.
Because the 4th side already exists, so wouldn't this not actually work? Let's give us like 4 equal sides.
What did, for our perimeter, what did we calculate? Didn't we calculate 2 x's, 2 x lengths, and how many y lengths? Is that still confusing?
Yeah, 'cause I thought that if you like, because I thought that a square would be like the most area, right?
Uh-huh.
So you could just divide 500 by 3,
Okay.
so that you'd have 3 equal sides, and then you would, the 4th side would be on the bar. And so I got a different answer.
What answer did you get?
I got 166.6.
166.6, which means that your y value has to be what?
But it's also 166.
They're both 166.
Yeah, because I was bringing up the length.
So this is 166.6, and this length here is 166.6, and this one here is 166.6.
Yeah.
So what volume do we get in here then? Can you?
Yeah. 27,777.
Did I write that right?
Yep.
Okay. So this is Emerson's argument. He's saying, why don't we take, if a squares tend to have the most area, so why don't we take this 500 And we're going to, since there's 3 pieces here, why don't we just divide it by 3? And then that will tell us what the lengths are of each one of the sides. And so, because there's only 3 sides here. So he took 500 divided by 3, and he got this value here. So if you add up all these, if you add up the perimeter now, this side here, plus this side here, plus this side here, that's going to give you 500. And so, and then for the volume, base times height will give us this volume here. So that is Emerson's suggestion. Let's go ahead and finish this and see if we can beat Emerson with a better area. Let's go back down here. We said that this side here is 125, which means this is also 125. What is the height then? Which is what? Louder? 250. What is the volume of this?
I'm so confused. How is the square not the biggest?
Because we didn't have to have this, we didn't have to, if we were trying to find an area where we had to build the perimeter for all 4 sides, then you're right, a square would be the perfect dimension to give you the maximum area. But we're not calculating, we don't need to find, or we don't need to fence all 4 areas. We only need to fence 3. So we're going to have a different outcome. If you add up all the sides, do we stay within that 500? Oops. This is 250.
Also the area is 31,200.
250?
Yeah.
Okay. 200. $250. So Emerson, you have to use calculus. Okay, so step me through how we did this. Emerson, were you right? Is this the strategy to use?
No.
No. So Emerson, step me through this one. How do we do it?
So we knew that we have 500 feet of fence, and we're trying to get the maximum area out of that with 3 sides. So we start off with the area equation, like x times y is the area.
Yep.
But we didn't want to use y, so we used the perimeter equation because we knew it was going to add up to 500 to find the y equal.
To substitute?
X, and then
Okay.
substituted that in for y, I mean, so that then we could have our area equation without having to have y in it. And then we found the derivative of that equation. And then we put in 0 for the derivative and solve for that, and then use the sign diagram to find out that way.
Okay. Are you, yes, sir, Andrew?
So if it was 4 sides, Emerson's method would be better?
Yes. It would be easier. Emerson's method would be easier if I had to find all 4 sides. Okay, and question? Do we get the same answer? Let's try that. Let's try it. Do we get Emerson's answer of 166.6 if we start out again? We have 500. Let me zoom in. So the answer is yes, but let's confirm it. Let's confirm it with calculus. Emerson, are you okay with that?
Okay.
Okay, so we're going to take 500 square feet and we're going to design a pen, all 4 sides. We'll call this X and this is our Y. And I want to find the maximum area. In this case, let's do Emerson's method first. Emerson, what would you do with your method?
So I know that if a square would have the most area,
A square has the most area, okay.
so then I would just divide 500 by 4.
Okay, so you take 500 divided by 4 to get 125. So we'd have 125 by 125.
Uh-huh.
Okay, those would be our dimensions. You're right. We'll find that answer to be correct by using calculus, but I want to go, we already know what the answer is. So I think it's helpful to still go through the steps of calculus to help it make those connections. So if I were to do this using calculus, what would I do? What's my first step? To use calculus to find the same answer.
I guess you do the area equation again.
Okay, my area equation, area equals x times y, okay?
I'll find the substitute for y.
Okay.
So I guess
The perimeter would be what?
the
2x plus 2y equals 500. Okay, we want to solve for one of these so we can substitute it in.
I guess you subtract the x from both sides.
Okay, so I have 2y equals 500 minus 2x. Okay, that gives me y equals 250 minus x. Are you okay with that? Okay, so I'm going to substitute that in. So that gives me that the area equals x times 250 minus x. Now what?
And then you could find, you
It starts with a D.
distribute.
Okay, so that gives me 250x minus x squared. Does that look right to you?
Yeah,
Okay, please correct me if I make a mistake. Now what?
and find the derivative of that.
Okay, if I find the derivative, that's going to give me what?
250 minus 2x.
Minus 2x, okay? Now what?
We'd set that to 0.
Set that to 0. 0 equals 250 minus 2x.
I add 2x to both sides.
Add 2x, so that gives me 2x equals 250, all right?
And then divide the sides by 2.
Does that give us our answer?
Yeah.
So why didn't your method work up here?
Because it was around on the sides.
Yeah, we were only finding the sides. We only needed to find 3 sides, or we needed the dimensions, or our pin needed to be designed with 3 additional sides because of the barn. Okay, let's do another one. Does that make you, Emerson, does that make you feel more satisfied?
Yeah.
Or at least down here? Okay. All right. We have, you need to design, this is our prompt, and I'm way too far out. You need to design a 1 liter can shaped like a right circular cylinder. What dimensions will use the least amount of material? When I say a right circular cylinder, I mean one that is not oblique. Now, there's something I should mention, that one of our conversions, 1 liter equals 1,000 centimeters cubed. Okay, where do I start? First of all, does everybody comprehend what the question is asking? I need to design this can using the least amount of material. Where do I start? Sorry, what? What's that?
The area of the circle times the height.
Yeah. So the volume, we're trying to figure out the volume of this cylinder, and the volume of a cylinder or the volume of all prisms are calculated the same way. Consider something else that might be a little bit more obvious to you when you look at a box. If this is still a prism, this is a rectangular prism. And if I can calculate what I don't know if it's going to let me, if I can calculate the area of the base, then let me use a different color. If I can calculate the area of this base, don't I just multiply it by the height? Because doesn't that base repeat itself over and over? Let's use a different color. Over and over and over as we go up the image. So we do this, so our formula for any prism is the area base times the height. Think of the cylinder. The cylinder has what kind of base? Yeah, it's a circle. And that circle, once we calculate the area base, then we just multiply that by the height, because that area repeats itself over and over again as you go up the cylinder. So the base of the cylinder is a circle. What is the area of a circle? Is it 2 pi r squared? There's something too much there that it's just pi r squared. It's just pi r squared. It's just pi r squared, but pies aren't square. Pies are round. I'm just trying to help you remember this. Pi r squared. But pies aren't square, they're round. Okay. Pi r squared times the height. Do I know anything about this? Do I know anything about this equation? Yeah, it has to equal this. It has to equal, I'm missing it. It has to equal 1 liter. 1 liter, our conversion right here is 1 liter is 1,000 centimeters cubed. And the reason I want to use this 1,000 centimeters cubed is because centimeters cubed, because I want to use 1,000 centimeters cubed instead of liters, because what are H and R measured in? Centimeters, not liters. So we're going to use that conversion of 1,000 equals pi r squared times the height. Okay, now what? Do we just take the derivative of this? Didn't I say when it comes to optimization that we usually have 2 equations we have to deal with? Yeah, we need the surface area. Why? What tells me when I look at this that I need the surface area? The material, yeah, the material, I'm trying to use the least amount of material. So let's consider what the surface of, if I have a sheet of metal, what needs to be cut out of the sheet to make a cylinder? All right, yeah, 2 circles, and then, yeah, just like the label around a can, if you undo the label, it's a rectangle. What do I know about the surface area? So I know that this area here is what? What's the formula for that? Okay, so that's going to give me pi r squared, and then we have 2 of those. So that in this case, it is 2 of these pi r squareds. And then what about the dimensions here? For a can,
Isn't it 2 pi r?
it's the circumference all the way around the circumference of our can. That's going to give us the bottom of this rectangle. So that's 2 pi r. 2 pi r. Okay, that's the circumference. What's this? Yeah, that's my height. So my surface area is what? 2 pi r squared plus 2 pi r times the height. Okay, now what? Solve for h for this one here. Which one of these am I going to take the derivative of? This, what tells me that I'm going to take this derivative of the surface area and not the volume? What in here in the question says I'm going to take the derivative of the surface area and not the volume? Louder? Yeah, I want the least material. I'm looking for the minimum for the material, not the volume. So I'm going to be taking the derivative of this, which means I need to solve for h for which equation? For the what? For the volume. So for the volume, I'm going to solve for h. So in this case, h equals what? 1,000 divided by pi r squared. And I'm going to substitute that right into here. So I have the surface area equals 2 times pi r squared plus 2 pi r times 1,000 over pi times r squared. Are you okay with that? What do I do from here? Okay, we could distribute. You're talking about up here? We could actually cancel some stuff here, right? If I cancel, what can I cancel? I can cancel out a pi and one of the r's, right? So one of the r's. So that's going to give me that the surface area equals 2 pi r squared plus 2,000 over r. Are you okay with that? Yes, no, maybe so. Okay, what do we do from here? Yep, just to make it easier to differentiate, we'll write it as 2,000 r to the power of what? -1, yep. So what's our goal? What are we trying to do? Trying to find the least material, which is a maximum or minimum. A minimum. with a slope of what? A minimum has a slope of what? 0. So I need to find my slope equation and then substitute in a 0. What is my derivative? What's the derivative? 4 pi r to -2. Okay, which is, sorry, equals 0. Okay, well, because we're trying to find a maximum, which is the same thing as using one of our laws of exponents, gives us this. How do we solve for r? Multiply by r squared to both sides. We would have to multiply this by r squared as well, right? Okay. So I'm going to multiply everything by r squared. What does the left hand side become? 0. What does this become? 4 pi r cubed. Okay. What does this become? Louder? Yep. Okay, now what? Okay, add 2,000 to both sides. It gives me 2,000 equals 4 pi times r cubed. Okay. 4 pi, so that gives me 500 divided by pi equals r cubed. Okay. Now what? What's the inverse of cubed? The cubed root. When we take the cubed root, do we need to remember plus or minus? No, why not?
Because even before
Yep, it only matters when your root is even. This is not an even root, it is an odd root, so we do not do plus or minus. So that's going to give me, then I have this r equals, should do that on both sides, the cubed root of 500 over pi. What does that give me approximately? Anybody have a calculator? What does that give me?
I got like 2.53.
2.53. Do I have confirmation that that's it? 5.4?
I think I may have forgotten.
What did you get? What did you get?
Oh, yeah, well, I got the 2.5.
I see.
Let me check. I also got 5.4.
5.4, okay, 5.42. So I have confirmation that it's 5.42. What's the rule for AP calculus? How many decimals? 3. So what should we write this as? 5.419, okay, 419. What are my units? Centimeters, okay. Is that my answer then? What was I asking for? What did I want you to find? I want the dimensions. I want the dimensions. So I found the radius. The radius right here is about 5.419. I still need to calculate the height. How do I calculate the height? Let me zoom out so we can see more of the stuff. We found that our answer is 5.419 as our radius. How do I find the height? How do I find the height? Is there any information here that would help me find the height? Eleanor? Yeah, it doesn't, yeah, right. I took this volume equation right here and didn't I already solve for H? So I could substitute that in. So what all we have to do is replace this R. Replace the R with what? Yeah. So our height becomes what? When we take this value and I take that and I plug it back in to our height equation, what does the height become? $840. What are my units? Yep. You get centimeters. Ellie, can you step me through this whole process of what we did? I don't want you to do the math. I just want you to talk about the logic. Tell me what we were thinking when we did this. So the goal is I need to design a cylinder, a circular cylinder that's 1 liter, that has a volume of 1 liter. Where do I start?
Okay, so you found that your volume is going to be 1 liter.
Okay,
And you're also seeing that
Hold
your
on.
volume is going to be the base times height. And then the area of the base is pi r squared, and then times the full volume of the cell.
correct.
So then.
So we found the volume. Now what was the next step?
Now,
Were we trying to find the derivative of the volume? Is that the goal?
no,
We're trying to find the volume of what?
or the material.
Of the surface area. So because that is material, right?
Mhm.
Okay.
So then you could calculate the surface area of the cylinder.
Okay.
So that was like the 2 circles on the top and bottom.
Uh-huh.
And then you have to find what you have to do substitution to find what the height was.
Uh-huh. Where did this come from?
That was from the 1000 equals 5 squared H.
Which is
So-
our volume, right? That was from the volume equation.
Yeah, so you just solve for that, and then you plug that in for H, and then you found the derivative,
And then we find the derivative of which equation again?
the surface
The surface area,
area.
good.
And then you set it equal to 0,
Okay,
and then you solve for the R, the radius.
good.
And then once you have that, then you're able to see the radius of the. And then you can use that radius to plug it into the height equation of the H equals 1000 squared.
Yep, and that gives us our dimensions, right? So our dimensions are what? What's the radius?
The radius is 5.41.
And the height?
Is
Nice, cool. When you do optimization, I want you to consider that you're most likely going to look at 2 different equations. And you need to decide based upon the problem, which of those you're going to be taking the derivative of, so you know what needs to be substituted in for what. This one is super easy. In fact, you could use Emerson's strategy for this one. I know we only have about 5 minutes left. You could use Emerson's strategy, but we really should use the calculus strategy to help us with this one. Here is the prompt. Here's our last one. I want to find two numbers. Oops. Two numbers whose sum is 20 and whose product is as large as possible. What does sum mean? It means addition. What does product mean? Multiplication. What are the two equations that we need? First of all, does this look like an optimization problem? Yeah, what tells me it's optimization? Large as possible. So we're looking at some value where we get to a maximum. We're looking at a maximum, which is an optimization problem. What is one equation? X plus y equals 20, because that's what we're saying here. Two numbers equal, or the sum of two numbers gives us 20. What's the other equation? X times y equals the largest number, a large number. Could you use Emerson's technique? Any guesses what that number would, those numbers would be, Emerson? 10 and 10. Yeah, they're 10 and 10. We're going to use this. So we know X is 10. How did you get X is 10 and Y is 10?
Because you have like the same idea, so it's they're as close together as possible. It's gonna be like.
Yeah, we could think of this multiplication as the area of a rectangle. And so our base times I, if we're looking at something the largest possible, we're looking at what are the dimensions of that square or that rectangle that will give us the largest area, and that would be a square. So you're right, it is 10. Can we figure this out using calculus? What do we do? Which of these do we take the derivative of? The first or the second? Why? It's because we're looking at the product that's the largest. And so that would be our maximum volume for the product, not the maximum volume for the sum. So we have two variables, Eleanor, so what do we do? Do we have to substitute something in? Okay, what are we going to substitute? If we don't need this equation for calculus, can't we do something with this equation to substitute it in? Yeah, so y equals 20 minus x. I just subtracted x from both sides. And so that's going to give me then x times 20 minus x. Does that look right to you? Okay, now what? Okay, if I distribute, that's going to give me 20x minus x squared equals L, my large value. Now what? Now we do the derivative, and the derivative of this would be what? 20 minus x, okay. And then? Okay, make this 0, so 0 equals 20 minus x. Is that, did we do the derivative of that right? Yeah, that would be 2x. Okay. 2x, right? So we have 0 equals 20 minus 2x, and then so negative 20 equals negative 2x, right? And x equals what? Which means y equals 10. Yep.